This video will introduce the Fourier transform, its mathematics, and talk a little bit about how we think about it. So you'll notice I've already put on the screen the definitions associated with the Fourier transform. So this first line is the Fourier transform. It takes a signal x of t, which is a time domain signal, and converts it into x of omega, which is the Fourier transform of this time domain signal. For those of you that are interested in this sort of thing, the Fourier transform typically has a capital letter to represent it, and you'll notice that the x over here is taller than the x over here. To take the inverse Fourier transform, I can use this formula. And you'll notice that the integral for this formula looks much the same as the integral for the forward transform, that is, going from the time domain to the frequency domain. Going from the frequency domain back to the time domain is actually pretty similar. I don't have the negative sign on the exponent, and I integrate with respect to omega. But again, given a transform x of omega, this will give me x of t. And I represent the fact that x of t and x of omega are related through the Fourier transform by this notation. Now, in terms of understanding how the Fourier transform works, the first thing to pay attention to is the fact that x of omega is generally a complex valued function of omega. So for every value of omega, this x will have a real part and it will have an imaginary part, which sometimes can be somewhat confusing. It also makes it quite difficult to graph x most of the time. So what we typically will do is we will define what's called the magnitude spectrum, and this is basically the magnitude of the complex value that x has. So again, the magnitude means that if I have a point in the complex plane, let's say this point right here, then the distance from the point to the origin is the magnitude. Okay. We will also define, I seem to have sort of run out of room, let's see if we can just tuck it in here, what we call the phase spectrum. And this is the angle that the complex number makes with the real axis. So in this particular case, if I have a complex number that's out here, the angle that it makes with the real axis would be the phase. Typically you express these phases in radians, and they'll typically have values that go from minus pi to pi. Again, because quite often we're mostly interested in the magnitude of the Fourier transform and how it behaves at different frequencies, we will plot just the magnitude spectrum. We'll plot just this guy, and then we'll talk about this as if it were the whole Fourier transform. Now, sometimes that's useful, but it's also technically wrong. In order to know what the whole transform is, I need to know both the magnitude and the phase of the Fourier transform, or equivalently, if I know the real and imaginary parts of the Fourier transform, that gives me the same information. To demonstrate how we deal with the fact that x of omega is complex, let's actually look at a specific Fourier transform pair. In the time domain, we have x of t is e to the minus at, and the u of t here just says that it's 0 for values of t less than 0. The Fourier transform of this, as you can easily compute, is x of omega is equal to 1 over j omega plus a. So we bring up FreeMat, my current MATLAB replacement of choice, and we'll use it to graph the real and imaginary parts of x of omega, and then the magnitude and phase parts of x of omega. So here we go. We set up first omega, and now we'll choose a value for a. Let's set a is equal to 2. Seems like a good one. Now we compute x, and this x is the Fourier transform. Okay, now we'll set up the plot. Okay, so this whole chunk of commands gives us then the following plot, which looks like this. And you can see that the real part of x of omega is symmetric about the point omega equals 0. It's an even function. It starts very close to 0, goes up to a half, goes back down very close to 0. The imaginary part, as a function of omega, is an odd function. It starts out here, goes up to about 2.25, and then goes down to negative 0.25. For any given value of omega, we could treat the corresponding real part and imaginary part as a complex number and get its magnitude. And in fact, that's what we do to get the magnitude as well as the angle plot for this function. So we'll do that next. So after getting all of the commands in to create the magnitude and phase plot, we have the following. This plot shows the magnitude. You can see that at 0 the magnitude goes up to 0.5, and then it tapers off as omega gets positive and tapers off as omega gets negative. The phase is 0 for omega equals 0. It asymptotically approaches negative pi over 2 as omega gets large, and asymptotically approaches pi over 2 as omega goes large negative. The Fourier transform, as we've just described it, is very closely related to the Laplace transform. So the Laplace transform has a definition that looks like this. This is the bilateral Laplace transform. And you'll notice that if I replace the s right here and here, actually we're replacing it here, by j omega, then I essentially have the same expression that I had before on the previous screen. X of omega is this integral from minus infinity to infinity, x of t e to the minus j omega t dt. So if I already know the Laplace transform of a particular time function, then I can find its Fourier transform very easily. So as an example, x of t is e to the minus at u of t. Those of you that have already studied Laplace transforms will know that the Laplace transform of this, x of s, is 1 over s plus a. Using this result that we've just looked at, we can say that x of omega is equal to 1 over j omega plus a. One last comment, and then we'll be done with the video. This x of t that we've used here is the impulse response of an RC circuit. And it turns out that we use these quite often as fairly crummy low-pass filters. If you recall, the magnitude spectrum was largest when omega is equal to 0, and then it tapers off as omega gets large, either positive or negative, which makes this, again, a crummy low-pass filter. So with that, we'll end this video. Thanks for watching.